Problem A3. Tilt shift. An ideal converging lens of focal length f is centered at x equals y equals 0 with its axis of symmetry aligned with the x-axis. A light ray incident at height y much less than f will be tilted inward by an angle theta equals y over f. In this problem, we will consider objects at x equals -0, where O greater than f. The lens will produce a real image of the object at x equals I, where 1 over O plus 1 over I equals 1 over f. Even for an ideal lens, the image of a finite-sized object will generally be distorted. Question A. Consider a point-like object at x equals -0 and y equals 0. If it moves to the right a small distance delta x, its image moves to the right a distance mx delta x. If it moves up a small distance delta y, its image moves up a distance my delta y. Find mx and my in terms of I and O. Question B. Suppose the object is a short stick, tilted an angle theta O to the x-axis. In terms of I, O, and theta O, what is the angle theta I its image makes with the x-axis? To produce a simple camera, we put the lens right next to a circular aperture of diameter d much less than f, and place a movable screen behind the lens. Suppose the location of the screen is chosen so that light from very distant objects will be focused to a point on the screen. Question C. The light from a point-like object at finite distance O will produce a finite-sized spot of radius r on the screen. Find r in terms of f, d, and O, assuming O much greater than f. Question D. If the camera primarily sees light of wavelength lambda much less than f and d, find a rough estimate for the additional spread r d of any image on the screen due to diffraction, in terms of f, d, and O. Question E. Assuming the typical numbers f equals 5.0 centimeters, d equals 5.0 millimeters, and lambda equals 500 nanometers, find the numeric values of O for which the blurring due to geometric effects exceeds the blurring due to diffraction. Real photos are noisy because light is made of discrete photons, with energy E equals hc over lambda. Suppose the camera is illuminated uniformly with light of intensity 1 equals 1 watt per square meter, its sensor has n equals 107 pixels, and every photon passing through the aperture is detected, with equal probability, by 1 pixel in the sensor. This implies that if the expected number of photons arriving at a pixel on the sensor is n, the standard deviation of that number is square root from n. Question F. If the aperture opens for time tau to take a photo, find the numeric value of tau for which the standard deviation of the brightness of each pixel is 1% of the mean.